Is my voice audible? We're gonna discuss. We're gonna continue the probability. So Markov chains. So in the previous session, we learned about Bernoulli and Poisson process. Bernoulli and Poisson processes we have seen so far are memoryless. That is, they did not depend on the present or past of the process. Now we are going to look at processes where the future is dependent on, and we can predict depend on the past of the process. So we deal such models by using state, which summarizes the effect of the past on future, which changes with time according to the given probability. So these processes in which states change at certain discrete time intervals, they can be indexed by variable n. So at each step n, the Markov chain has a state denoted by xn, which belongs to finite set of S called state space. So we assume S to be a set of m natural numbers. The Markov chain is described in terms of transition probabilities, that is denoted by Pij, where it is defined as probability of the state j given that the previous state is I. So Pij is represented by P xn equal to j given xn minus 1 equal to I. So this is in most of the cases in the questions also you will be given the transition probabilities only to find the probability of the probability of the Markov chain model. So the main assumption underlying the Markov process is that the transition probability just depend on the state immediately past or preceding the state. So now that is P of j n xn equal to j depends on only xn minus 1 equal to I. It is independent of xn minus 2, xn minus 3 and so on till 1. So we can conclude that this is equal to P xn equal to j, xn minus 1 equal to I. So this is Pij. Thus the probability law of the next state xn equal to j depends on the past only through the value of the present state xn minus 1 equal to I. So it only depends on the previous state, not the xn minus 2, xn minus 3. So we observe that Pij is always greater than 0 since probability is always greater than 0. And the sigma j equal to 1 to m, Pij is 1 for every I. We will allow Pii is greater than 0 in general. This is the current state can be always retained by such transition. I mean, it can be in the state only for the next state also. So we can say that is self transition. So generally, transition probabilities of a given set of n states can be represented in terms of matrices and graphs also. Simply a two-dimensional array where the element in ith row and jth column is Pij. Before only we discussed Pij is a probability of xn equal to j given xn minus 1 equal to I. So it can be represented as a matrix. So this is the matrix Pij. So if we want to represent this transition probabilities in a graph, in the graph, we generally have vertices or nodes and arcs. So in this graph, the nodes are states and the arcs are possible transition between the nodes by recording the values of Pij near the nodes, and we can visualize the entire model. So let's see an example. So Anjali is taking a probability class, and in each week, she can be up to date or she may have fallen behind. If she is up to date in a given week, the probability that she will be up to date or behind in the next week is 0.8 or 0.2. If she is behind in the given week, and the probability that she will be up to date or behind in the next week is 0.6 or 0.4. So let us observe. Here we can observe that the probability that she will be up to date in the next week depends on the depends how she is in the given week. So it is obviously a Markov chain. So identifying the states, now we have to define the states, like up to date we can define it as state 1, and behind we can define it as state 2. So there are two possible states. Now in the question we have seen, if she is up to date in the given week and up to date in the next week, it is P11. I mean, being in the, it is a self transition, so it is 0.8. Now, if she is up to date in the given week and if she is falling behind, it is P12. So we can take that as 0.2. And if she is behind in the given week and if she is up to date in the next week, it is 0.6. So P21 is 0.6. And the probability that she is behind in the given week and in the next week is 0.4. So that is P22. So we can represent this as a matrix. And now if we consider a graph, transition probability graph, so we can state 1 and 2 are marked as nodes, and the arcs representing the transition probabilities of the respective transitions. Is everything clear? It depends on how you take the up to date and behind. Whatever you choose, you just mention it before so you can understand. Anything is fine. So now multiplication rule and probability models. Now P of x0 equal to I0, x1 equal to I1, and xn equal to In. P equal to Px0, x0 equal to I0, and probability transition probabilities, multiplication of transition probabilities. This we can just, it's just a mathematical operation. We can write Px0 equal to I0, x1 equal to 1 as Pxn given In, Pxn equal to In given x0 equal to I0 and so on, into P x naught equal to I naught and so on, n minus 1. So we observe here this pxn equal to in only depends on the n minus 1. So directly we can ignore these all terms. So it is directly pin minus 1 and in. Since pxn equal to in, xn minus 1 equal to in minus 1 is probability transition of the from n minus 1 to n state. So we can directly write as pin minus 1 in. So p and directly we'll multiply this, and again we write this as xn minus 1, xn minus 1 equal to in minus 1, given x naught equal to I naught and so on, xn minus 2. And again that and n minus 1 state will only depend on n minus 2. So we ignore the other terms. So we'll get this equation. P of P x naught equal to I naught, x1 equal to I1, xn equal to In equal to P of x naught equal to I naught, P multiplication of the probability transitions. Is everything clear? Now we move to n-step transition probabilities. Many Markov chain problems require the calculation of probability law of the state at some future time conditioned on the current state. Probability law captured by the n-step transition probabilities is defined by Rijn, which is equal to probability of xn equal to j, x not equal to I. It means you are the current position, the current state you are in is I, and j be the state after your n. So this probability can be calculated by this n-step transition probability defined by Rijn, which is equal to P of xn equal to j given x not equal to I. So Rijn can also be thought as the probability that the state after n time periods will be j, given that current state is I. Now we'll see Chapman-Kolmogorov equation. This is generally based on the induction. So the n-step transition probabilities can be generated by the recursive formula Rijn equal to sigma k equal to 1 to m Rik n minus 1 p. So this we can we can consider as we can the n-step transition probability. Now, according to this equation, this is the probability of calculating the n-step transition probability. That is, you are in your present or current state is I, and after n steps, your state is j. So probability of the probability of the n-step transition is given by Rijn. So this you can consider the probability of n steps. So we see that what is the probability to reach j in one step after n minus 1 steps already done. So you can be at a state k of n minus 1. After that, n minus 1 steps again, the probability of n minus 1 steps from I to k is given by Rik n minus 1. And from there, you can reach state j with probability pkj. So for the total probability, we should take all the possible values of k. So it is just like induction. So choose any of the state k. So you have n minus 1 steps from I to k. So that probability is Rik n minus 1. And from k to j, probability is transition probability pkj. So the total probability will be multiplication of both, and sigma will go from 1 to m. So this is for all n greater than 1. And if I and j, only one step is there, that is obviously the transition probability Pij. So now we'll discuss about classification of states. So first we need to define a term called accessible. So we say that state J is accessible from a state I if for some n steps, the n step transition probability is greater than 0 and there is a positive probability of reaching J starting from I. It means you must have, you should be able to reach J from I. That means you just need to have transition probability also greater than 0. In other words, we can say that there is a possible state sequence I1, I2, In minus 1, J that starts at I and ends at J, in which transitions I, I1, I1, I2, all these have positive transition probabilities. Accessibility is just nothing but you should be able to reach J from I in any of the paths. We'll discuss examples later. Any doubts till now? If you have any doubts, you can just put in the chat or so now we'll start with recurrent and transient states. So let AI be the set of states that are accessible from I. So AI be the set of states that are accessible from I. That means it should be the elements in the AI should be reachable from I. So we say that I is recurrent if for every j that is accessible from I is also accessible from j. So it should be from both sides. You should be able to go from I to j and j to I. So such states are called recurrent states. For all j, so we can define it in another way also. For all j that belongs to AI, we should have I belongs to aj. So such states are called recurrent, and the state that is not recurrent is called transient state. So now we'll look at an example. So now here, one is accessible from 2 and from 1 itself. But since 1 is accessible from 2, but 2 is not accessible from 1, so 1 itself is a transition. 1 itself is a recurrent state. So now we take state 2. states 1, 3, 4 are accessible from 2. So you can go to 1 from 2 like this, and to 3 from 2 like this, and 4 you can go from 2 to 3 and 3 to 4. But 2 is not accessible. Now you can't go to 3. You can't go from 3 to 2. So state 2 is transient. Now we observe state 3 and 4. They are accessible from each other. You can go from 3 to 4 and 4 to 3. So these two form a recurrent class. Now, if I is a recurrent state, the set of states AI that are accessible from I form a recurrent class, or you can simply call it a simple class uh, that says states in AI are all accessible from each other. So in the previous case, you observe 3 and 4. You can now 3 and 4 are a class. So 3 is accessible from 4 and 4 is accessible from 3. So the 3 and 4 form a recurrent class. And 1 itself form a recurrent class. So here are some few points about Markov chain decomposition. A Markov chain can be decomposed into one or more recurrent classes plus some transition states. In the previous example also, we have seen two recurrent classes and one transition state. A recurrent state is accessible from all states in its class, but it is not accessible from the recurrent state in the other classes. So you can see now 1 is a recurrent class and 3, 4 together form a recurrent class. So, but 3 is not accessible. 3 is not accessible from 1. So that concludes this point, that recurrent state is accessible only from the states within its class. It is not accessible from recurrent states in the other classes. A transient state is not accessible from any recurrent class, because if it is accessible, it will also become a recurrent class, right? So transient state is not accessible from any recurrent class. At least one or possibly more recurrent states are accessible from a given transition state. Now we'll look at these examples. So in the first case, you observe 1. You can so from 1 you can go to 2 in this way, and from 1 you can go to 4 in this way, and from 1 you can go to 3 in 2 steps, from 1 to 4 and 4 to 3. So for 1, it is from 1 you can go to any state. If you observe 2 also, from you can go from 2 to 1 in this way, and 2 to 3 you can go in 4 steps. 2 to 1, no, in 3 steps: 2 to 1, 1 to 4, and 4 to 3. And from 2 to 4 you can go in 2 steps, that is 2 to 1 and 1 to 4. So now we look at state 3. You can go from 3, you can go, yeah, you can go to 1 from 3 to 2 and 2 to 1. And you can go from 3 to 2 in 1 step, 3 to 2, and 4 directly in this way. So 3 is also accessible from all the states. Now we look at 4. You can go from 4 to 1 in this way in 3 steps. 4 to 3, 3 to 2, 2 to 1. And 4 to 2 also you can go in 2 steps. 4 to 3, 3 to 2. So in this case, all the 4 states are accessible from all the other 3. So this is a single class of recurrent states. So each of them will be accessible from the all the other 3. Now, now from 1 you can go to 2, but you can't. But can't have the 1 and 2. So 1 and 2 will form a class. 1 and 2 will class 3 transient state, because you can't leave 2. Uh, 1 and 2 are from each other. So they form a single class of recurrent and transient state 3. Now you consider this example. Uh, so one is accessible only from itself, and it can be accessible from 2 to 1, but there is no possibility of going from 1 to 2. Okay. Generally, now in this example, okay, in this example, one is reachable from 2, but 2 is not reachable from 1. So 1 separately forms the recurrent state because it have because it is accessible from itself. So it is a recurrent state of now we consider um, 2, 3 is reachable from 3 is reachable from 2. So now we'll go through the slides once more. Markov chain decomposition. A Markov chain can be decomposed into, it can be decomposed into recurrent classes and transient states. So if we consider a recurrent class, uh, each of the recurrent state in a class will be accessible from all the state within the class, and it is not accessible from the recurrent states in the other class. So a transient state is not accessible from any recurrent state. At least one, possibly more recurrent states are accessible from a given transient state. Have any doubts regarding this? So now we'll see this third example. We have seen that one is accessible from two, but two is not accessible from one, and one is accessible from itself. So it will form a recurrent state. Now we consider two. Two is accessible from itself, but it is not accessible from one. It is accessible from three, and three is also accessible from two, but three is not accessible from itself. So 2 and 3 will become transient states. Now when you consider 4 and 5, 4 and 5, they are accessible from each other. So 4 and 5 will be a recurrent state. Two classes of recurrent states, 1 and 4, 5. These two are transient state, 2 and 3. So now we'll discuss periodicity of recurrent classes. A recurrent class is said to be periodic if the states can be grouped in D disjoint subset S1, S2, and so on St, so that transitions from one subset leads to the next subset Sk plus 1. That is, if I belongs to Sk, Pij is greater than 0, then J belongs to Sk plus 1. If k equal to 1, 2, and so on d minus 1, if it belongs to S1, k equal to 2. That is self-transition. A recurrent class that is not periodic is said to be aperiodic. We can go through one example. Now, we consider this as a subset 1, 2, and 3. Now, as we defined here, if all the states grouped in D disjoint subsets so that all the transition from one subset leads to next subset. So if you see from here, all the transition from one leads to S2. All the transitions from one leads to the states which are present in S2, and all the transitions from 2 also lead to the states which are in S2. And now if you consider S2, 3, 4, 5, the transitions from 3 leads to 6, which is in S3. If you consider 4, all the transitions from 4 leads to 6, which is in S3. And all the transitions from 5 leads to 6, which is in S3. And now if you consider 6, all the transitions from 6, that is 6 to 2 and 6 to 1, lies in the subset 1. So if we are able to divide the states into such subsets so that all the transitions from one subset leads to the states in the other subset, it is called a periodic recurrent class. So now we'll discuss about steady state probability. So for every state J, the nth step probability Rijn approaches to a limiting value that is independent of I, where we exclude two situations. We will exclude two situations in this case: multiple recurrent classes and periodic multiple recurrent classes and periodic class. This limiting value is denoted by pi ij, which has an interpretation called steady state probability of J. So we discussed before that n step probability of Rijn is probability of reaching J from I in n steps. That is, your current state is I, and after n steps you reach J. So the total probability is given by n step probability Rij. In this case, it approaches a limiting value that is independent of I. In such In such conditions, we assume this limiting value denoted by pi ij, which is steady state probability of j. But here we exclude multiple recurrent classes and periodic classes. So before you apply this, you just have to verify that it is not a multiple recurrent class and a periodic class. So as we told, it is independent of I. So pi ij is probability of xn equal to j, where n is large. To steady state convergence theorem. Now we consider a Markov chain with S, which is aperiodic, because we told that it should not be multiple recurrence periodic. So then the states J are associated with steady state properties pi j that have the following properties. So as n is large, that is limit n tends to infinity, the total probability of reaching j from I in n steps will be equal to steady state probability of j. This is for all I and j. So it is independent of I as n is large. So we can write limit n tends to infinity rij n equal to pi ij for every I and j. So here we also come up with pi j are unique solutions of system of equations pi ij equal to sigma k equal to 1 to m pi k and probability of transition probability from k to j. So this is so pi 1 if you consider a Markov chain of three states 1 2 3. So pi 1 pi 2 pi 3 will be the solutions of the system of equations pi 1 equal to sigma k equal to 1 to 3 pi k p kj. We'll see this in the further examples. So for transition states pi j equal to 0 and pi j is greater than 0 for all recurrent states. So the steady state probability pi j will sum up to 1. Uh, like if you take a Markov chain of two states, 1 and 2, pi 1 plus pi 2 will always be 1. Because they contribute on the whole state space. So to find pi 1 and pi 2, we have another equations that is pi j equal to sigma k equal to 1 to m pi k p kj j equal to 1 2 3 and so on m, and these equations are called balance equations. So you can try this out for 5 minutes, and if you get the answer you can put it in the chat. So here you're already you're already given the transition probability from 1 to 1, 1 to 2, 2 to 1, and 2 to 2. You just need to apply the balance equations and this pi 1 plus sigma pi ij for every j equal to 1 to m equal to 1. So once solve the equations and try to find the steady state probabilities pi 1 and pi 2. Let's see how it works. So we take the balance equations pi 1 equal to pi 1 into p11 plus pi 2 into p21 and pi 2 equal to pi 1 p12 plus pi 2 equal to p22. And we already know that pi 1 plus pi 2 equal to 1. So you just put p11, p11, p12, p21, p22 values in the equations. You get pi 1 equal to 0.8 pi 1 plus 0.6 pi 2, pi 2 equal to 0.2 pi 1 plus 0.4 pi 2. So solving these two, you get pi 1 equal to 3 pi 2. And we already know that pi 1 plus pi 2 equal to 1, which gives you pi 1 equal to 0.75 and 0.25. So this is how we calculate the steady state probabilities when you're given the transition state probabilities. And is this okay? Let's move to this. So here we can this equation we have already seen in the Chapman-Kolmogorov equation. Rij equal to sigma k equal to 1 to m Rik n minus 1 pkj minus kj. This is just as I already explained. It is the probability of reaching j from I in n steps, which can be calculated by the recursive equation. So when you take the limit of these equation on the both sides, we get the balanced equations. That is, if you take n tends to infinity, you get the LHS R j, that is pi j. I mean, if n is very large, it is independent of I. So Rij will become pi j. And since n is too large, n is almost equal to n minus 1. So that Rik part also will become pi j, pi k, sorry. So we'll get this equation. Pi j equal to sigma k equal to 1 to m pi k and p kj, where j is from 1 to and so on m, and you can take k from 1 to m. So now in the similar way, consider a two-state Markov chain with transition probabilities, that is P11, P12, 21, Q2. Now find steady state probabilities pi 1 and pi 2. Can anyone try this? You just have to write the balance equations and pi 1 plus pi 2 equal to 1. In a similar way we did before. Okay, let's see. So we just have to take the balance equations. Pi 1 equal to pi 1 into P11 plus pi 2 into P21 and pi 2 pi 1 into P12 plus pi 2 into P22. And we already know that pi 1 plus pi 2 is equal to 1. So we just put the values of P11 and P12, 21 and 22 from here. And you get these two equation. When you solve them, you'll get pi 1 equal to 2 pi 2. And you have the equation pi 1 plus pi 2 equal to 1, which gives pi 1 equal to 2 by 7 and pi 2 equal to 5 by 7. So now we'll go with this problem. Ashrita has two umbrellas that she uses when commuting from home to office or back. Transition probability graph is given below. Suppose that it rains with probability P each time she commutes independent of the other time. Where state I mean, you can define state I as I umbrellas available. So what is the steady state probability that she gets wet in a given day? So you can try this out. So here you find three possibilities that she have zero and she have left with no umbrella, she have one umbrella and two umbrella. So these number of umbrellas available that can be considered here as state. So you're already given a clue there. So what is the steady state probability that she gets wet in a given day? So once I'll give you 5 minutes, you just try out this. I'll repeat the question once more. Ashta has two umbrellas that she uses when she's commuting from home to office and back. The transition probability graph is given. Suppose that it rains with probability P each time she commutes. So here we consider state I as I umbrellas available. What is the steady state probability that she gets wet? That is now, suppose if she's going from home to office and she have zero umbrella, but when she is returning from office to home, she have two umbrellas. That probability of that transition state is 1, which is given here 0 to 2. So I mean, you can consider, so now if you consider that she is having two umbrellas when she's going from home to office, and then she's when she's coming back office to home, she have only one umbrella. The probability of that transition state is P. So now we have to find the steady state probability that she gets wet in a particular day. Considering that probability of raining is P. Just try out for 5 minutes, then I'll go with the solution. Okay, now look at the solution. So, so before applying this steady state, you just need to verify if it is uh, periodic or recurrent class. So this chain is a single recurrent class, that is a periodic. So we can apply steady state convergence law. Now we write balance. Now we'll write, first of all, we'll write the balance equations. Pi naught equal to 1 minus p into pi 2. You can write these equations from this graph given here. So you'll have these three equations, and the final equation pi naught, pi 1, pi 2 equal to 1. Here we consider the states 0, 1, 2 because we are considering I umbrellas available. So zero umbrellas, zero umbrella, one umbrella, and two umbrellas. So we consider pi naught, pi 1, pi 2. Now when you solve these equations, you'll get pi naught, pi 1, and pi 2. So the steady state that Ashita finds herself in a place without an umbrella is pi naught. So is pi naught, and the probability that she will get wet is pi naught into p because they have given that it rains with probability p each time she commutes independent of other times. So when she have no umbrella, she'll get wet. So the steady state that Ashita finds herself in a place without umbrella is pi naught. So the probability that she gets wet is pi naught into p. So now steady state probabilities as expected state frequencies. For a Markov chain with a single class that is aperiodic, the steady state probability pi ij satisfies pi j equal to limit n tends to infinity Vij n by n, where Vij is the expected value of number of visits to state j starting from I within first n transitions. So there will be two assumptions. I mean, when you consider n tends to infinity, one is this and one is the next one. So the steady state probability will be equal to limit n tends to infinity Vij, where Vij is expected values of number of visits to state j from state I within the first n transitions. You just need to remember this. In most of the questions also you'll not go through this. Expected frequency of a particular transition. Now we consider n transitions of a Markov chain with a single class that is aperiodic, and starting from a given initial state, here we define Qik be the expected number of such transitions from J to K regardless of initial state. So in the previous case, it was like you define the initial state I and you go to J in V steps, V visits or V steps. But here it is independent of initial state. You just need to go from J to K regardless of initial state. So that limit divided by n is equal to pi j into transition probability from J to K. You just need to remember these two equations. So the main application of Markov chain is birth-death process. So a birth-death process is a Markov chain in which the states are linearly arranged and transitions can occur only to a neighboring state or else leave the state unchanged. That means from 0, you can see here, it is accessible from itself or from the neighboring state 1. So 1 is also accessible from its neighboring states 0 and 2 and itself. So such Markov chains are called birth-death Markov chains. This arises in many situations, especially in queuing theory. So general structure of this is given here. So from 0, you'll have one B naught. From 0 to 1, you will have B transition probability B naught. So we generally know that pi 1 plus pi 2 equal to 1. I mean, pi sigma Pij equal to 1. So if this is B naught, obviously this should be 1 minus B naught. So when you consider 1, B1 and D1, so it will be 1 minus B1 D1 and so on. This is the general structure of the Markov chain. So here, when we consider the balanced equations, we get further simplified equations that are pi I bi equal to pi I plus 1 di plus 1. So they look similar to the balanced equation, but they are further simplified. So they are so these equations are called local balance equations. So you just need to remember these two. Pi I bi equal to pi I plus 1 di plus 1 for I 0 to m minus 1. Pi I equal to pi naught into b naught b1 and so on bi minus 1 by d1 d2 and so on di, where I is from 1, 2, 3 and so on. So this is just an application of Markov chain. You can directly remember these two equations and you can solve the questions. So here we conclude Markov chains. If you have any doubt, I'll wait for 5 minutes. If you have any doubts, you can ask in the chat. Okay, now we'll start with the limit theorems. So we consider a sequence of random variables x1, x2, and so on xn, which are independently identically distributed with mean mu and variance sigma square. So now we define a term Sn, which is the sum of the random variables. That is Sn equal to x1, x1 plus x2 plus and so on xn. As they are independent, we can directly add up the variance also. So variance of Sn equal to variance of x1 plus variance of x2 plus variance of x3 and so on variance of xn, which is equal to n into sigma square. So now we can say that the distribution of Sn spreads as n increases, which doesn't seem meaningful. So I mean, if you increase the value of n, Sn also increases. So we need so we define a sample mean Mn, which is equal to x1 plus x2 and so on xn by n, which is equal to Sn by n. So here the expected value of Mn is mu naught. And the variance of the Mn is sigma square by n, because if you divide n inside the bracket, outside you need to divide by n square. So you'll get n. So the mathematical interpretations of the above terms leads to limit theorems. So why do we need limit theorems? Conceptually, they have an interpretation of expectation values in terms of long sequence of identical independent experiments, random experiments. So they allow approximate analysis of properties of random variables such as Sn, and to evaluate PMF and DMF of Sn where n is too big or large. Now we consider quantity, which is intermediate between Sn and Mn. So we first subtract n times mu from Sn to obtain a zero mean random variable, because expected value of Sn is n into mu. So for the random variable Sn minus n mu is expected value of Sn minus n mu is 0. And then you divide by sigma into root n to obtain a random variable Zn of mean 0 and variance 1. So we define Zn as Sn minus n mu by sigma into root n, where the expected value of Zn is 0, variance of Zn is 1. Since here, whatever the value of n be, mean and variance doesn't change. So its distribution neither spreads nor shrinks to a point. So with this asymptotic shape of distribution Zn, we define central limit theorem. So this is the standard normal random variable central limit theorem. Let x1, x2, and so on xn be the sequence of independent, identically distributed random variables with common mean mu naught, mu, and variance sigma square. So we already defined Zn equal to Sn minus n mu by sigma into root n. Sn is the sum of the random variables. So here in the central limit theorem, whatever the value of n be, the mean of the Zn is 0 and variance of the Zn is 1. And you can get that by these mathematical operations. Expected value of ax plus b is a into e, expected value of x plus b, variance equal to a square times the variance of x. So on the practical side, central limit theorem eliminates the need for detailed probabilistic models and for manipulations of PMFs and PDFs. So as the value of n increases, it will become difficult to calculate the PMF and DMFs. So rather we simply refer to normal CDF. CDF means a cumulative distribution function. In a probability theory and statistics, the cumulative distribution function of a real valued random variable x evaluated at x is a probability that x will take values less than or equal to x. That is, CDF is represented by capital F x equal to probability of the random variable which is less than x. So here we approximate the calculations to the normal CDF. So CDF of a Zn. CDF of Zn converges to standard normal CDF. So as normal and Gaussian random variables discussed in the last session, just you can go through this. Random variable is said to be normal or Gaussian if it has PDF in the form of 1 by sigma root pi into this. So here we consider mu equal to 0 and sigma equal to 1. We get this equation. Pi, which is probability y less than y equal to 1 by root pi minus infinity to y e power minus t square by 2 dt. So this is what I have written here. CDF of Zn converges to standard normal CDF, which is equal to 1 by root pi minus infinity to z e power minus x square by 2 dx. In sense that limit n tends to infinity, this probability of Zn less than n is equal to the normal CDF for every value of z. So approximations based on central limit theorem. The central limit theorem allows us to calculate probability related to Zn as if we take Zn is a random normal variable. Since normality is preserved under linear transformations, like which is equivalent to treating Sn as a normal variable with mean n mu, and then you can subtract n mu and divide by sigma root n. So let Sn, we already defined Sn as the sum of random variables where the xi are independently identically distributed random variables with mean mu and variance sigma square. If n is large, the probability Psn less than C can be approximated by treating Sn as if it is a normal variable by following procedure. So now we will first calculate the mean n mu and variance n sigma square of Sn. Then we'll calculate the normalized value Z, which is C minus n mu by sigma root n. Then we'll use the approximation that probability of Sn less than C is equal to normal CDF, which is 1 by root 2, 1 by root of 2 pi into integration of minus infinity to z e square e power minus x square by 2 dx. So here are a few conditions of CLT. So we know that central limit theorem states that sampling distribution of mean will always follow a normal distribution under few conditions. So for calculating anything, we can just approximate it to the normal distribution. So sample size is sufficiently large. This condition is usually met if sample size is n greater than or equal to 30. Samples are independent and identically distributed random variables with the same mean and variance. So the population distributions have finite variance. CLT is not applicable to the distribution with infinite variance. So as we discussed before, CDF is the sum of the probabilities for y less than or equal to small y. So these values will be given in a table. So the leftmost table is integration from 0 to z, and the rightmost one is from minus infinity to z. So it is just the area under the standard normal curve. So if in the problems when you're calculating, you just need to take the values from here.